So first of all, are there any questions from last time before we get started? If not, then first of all, I'm going to just recall the last thing which we did. So we used this formula for relative entropy. So we can think of it as a formula for the relative entropy between two states for measurements in some region of space-time. So the last thing we did was to use it to prove that relative entropy is positive. And recall that if there are density matrices, then we showed that S psi phi would be the trace of rho log rho minus log sigma. So this included a new proof of positivity of relative entropy in the usual case of quantum mechanics where density matrices can be assumed. But the proof, well, apart from being short once you've defined the modular operator, the proof had the advantage that it was more general, and in particular it applied in quantum field theory. Today, however, we're going to prove a much deeper result. Monotonicity of relative entropy. So, in the usual quantum mechanical setup, you have a system and a subsystem. So, the usual, I've explained this many times, but the usual statement is like so. But we're going to prove a version of this when the two systems correspond to two regions of space-time. There's U and there's a smaller region V. V is contained in U. And now we could define the relative entropy in region V or the relative entropy in region U. And the claim of monotonicity of relative entropy is that the relative entropy is bigger in the bigger region, or generically bigger, but strictly not smaller. So our first goal today is going to be to prove that. Now, this statement is just the expectation value in the state psi of an operator inequality. The operator inequality is at minus log delta psi phi of region V is less than minus log delta psi phi of region U. So we're going to aim to prove this inequality, and then just by taking its expectation value in the state psi, we'll get the inequality among relative entropies. Now, a fact we've used before is that for operators as well as numbers, log x is the integral from 0 to infinity dt of 1 over t minus 1 over t plus x. So an equivalent statement it's not exactly equivalent. So this follows from what's actually a stronger statement, that 1 over t plus delta psi phi of v. I want to write it up higher where everybody can see it better. So just here. Also, where I'll be less likely to erase it. not 1. I'll state this with t. This is for all positive t.
There's t plus 1. Is it 1 over t plus 1 there?
Oh, thank you. Thank you. It's good to have people paying attention so I don't get rid of, commit sins like writing down a divergent integral and claiming it equals log x. Okay. So this is our formula for log x. So we're going to prove this inequality. So our goal in the next 10 minutes or so will be to prove this. And then by integrating over t in this handy formula, that gives an inequality among the logarithms of the operators. And monotonicity of relative entropy is merely the expectation value of that last inequality in the state psi. So all we need to do is to prove this inequality. Any questions about that? So the first step is to slightly improve the definition of S. Well, I gave a definition that was good enough for what we've done so far, but we need a slightly better definition to go forward. We said that if A is an operator in region U, then we defined S psi phi of U, which I'll just call S psi phi for notation. I don't want to keep writing U. We said that S psi phi acting on A psi was equal to A dagger phi. Now, we're going to keep that, but we're going to add certain limits of that statement. If x is the limit as n goes to infinity of an psi, and y is the limit as n goes to infinity of an dagger phi, then we say that Sx is equal to y. So in other words, we add pairs like this. Sorry, we add limits of pairs like this. If we take a limit of these guys that converges, you see, the large n limit of an on psi may exist as a vector, even though the limit of an does not exist. If the limit of an and an dagger existed, we wouldn't be saying anything new. But it can happen that the vectors an psi and an dagger phi have large n limits, even though the operators don't. And if that happens, we want to slightly extend the definition of S psi phi so that basically we define it in any vector where we know what the answer should be. So if a vector is the limit of an psi, and we know what S does in an psi, we naturally want to define S to map to the limit of these guys, assuming that limit exists. It's a little bit embarrassing to explain a technicality like this in a physics course, I'm afraid. But we kind of need it. Now, what that did is to ensure that pairs X, Sx. Consider all pairs. Look at all pairs X, Sx, where Sx is defined. X is in our Hilbert space, and Sx is defined. So this is a pair of vectors in, at the moment, in H plus H, so we'll change that in a moment. Now, what we did was we added limits of such pairs whenever possible. So we ensured that such pairs are a closed subset of H plus H. We made it closed by just adding limits whenever possible. A closed subset contains all limits of sequences that converge. So if you have a sequence of x's and sx's which converge in H plus H, we want to define S so that this is such a pair. So we're now talking about a closed subset of H plus H, but it's not a linear subspace. Since S is antilinear. So you see, if lambda is a complex number, our subspace would contain that vector, not this one. So this isn't a space where we can multiply by a complex scalar, so it's not a complex vector space, subspace. It is just a closed subspace. However, to express the argument we're going to make in a more familiar language, I want to turn this into a linear subspace. And there's a small trick to do that. So I'm going to define the complex conjugate of a Hilbert space. So if H is a Hilbert space, then H bar is a new Hilbert space. It has the same vectors. So if V is in H, I'll write V bar for the corresponding vector in H bar. And there's just a one-to-one correspondence between vectors V and V bar. But the rule is that lambda V bar is lambda bar V bar. So if you take a vector in H and multiply it by lambda, the corresponding vector in H bar is lambda bar times the vector corresponding to V. Obviously, the definition has been made to make this formula look natural. Now, the point of that is that I define S as an antilinear operator from H to H. But that's the same as saying that S is a linear operator from H to H bar. I just map x to the vector in H bar that corresponds to Sx. And that's a linear map from H to H bar. So we now look at pairs x and Sx regarded as vectors in H plus H bar. And it's still a closed subset, but now it's a linear subspace. So such pairs were a closed subset of H plus H, but they're a closed subspace of H plus H bar. Closed subspace means a Hilbert subspace. We have a big Hilbert space, H plus H bar, and such pairs are a subspace. So I'll call that subspace are a Hilbert subspace Ku in H plus H bar. Now that was assuming that we considered the modular operator for the region U. Of course, we could have considered the modular operator for the region V. Then we'd have gotten another subspace in K sub V in H plus H bar. Now, SU, well, S psi phi of the bigger region U is defined for all vectors on which S psi phi of V is defined. You see, S psi phi of V was defined by saying that it takes A psi to A dagger phi if A is in the region V. S psi phi of U was defined by the same rule, but now A is in the bigger region, U. So this operator is defined whenever this operator is defined, and on any vector in which this operator is defined, this one agrees with it. And that was true after we took limits. If we have a limit of these things, so that we then defined S psi phi V on some additional vector that wasn't quite given this way, the same limit existed over here. So one operator is what would be called an extension of S psi phi of V. That means it's defined for all vectors. The extension, this one, is defined for all vectors where this one is defined, and where they're both defined, they agree. But this one is defined for more vectors. Now, this situation might sound unfamiliar because it can't happen in finite dimensions. In infinite dimensions, there's no problem. For example, you could think of the operator d by dx on the unit interval, and then we could let operator A, it acts on smooth functions on 0, 1. Operator B acts on smooth functions that vanish on the boundary. So A is an extension of B. If we consider the Hilbert space of L2 functions on 0, 1, first of all, unbounded operators are always only defined on a dense subset of Hilbert space. So both A and B are defined on dense subspaces, because smooth functions and also smooth functions that vanish at the end are both dense in Hilbert space. For example, for the ones that vanish on the end, you all know that sine functions, sine pi nx, are dense, or are Hilbert space basis, and they all vanish at the endpoints. So they're all smooth functions that vanish at the endpoints. So operator B is defined on a whole dense subspace. Well, on a basis, I should say. And also on a whole dense subspace, therefore, since it's defined on a basis. So these operators are different, even though one is an extension of the other and they're both defined on a dense subspace. Now, the inequality we're trying to prove is true whenever that's the case. A being an extension of B will imply this. So in other words, everything I'm going to say beyond that point is just going to be a general explanation that if A is an extension of B, then 1 over t plus b dagger b is less than 1 over t plus a dagger a. In my example, if you think it through carefully, you'll discover that b dagger b is the Laplacian with Dirichlet boundary conditions, and a dagger a is the Laplacian with Neumann boundary conditions. And Dirichlet boundary conditions make the energy bigger because they force the wave function to vanish. So in this example, the meaning of the inequality is that the forcing the wave function to vanish at the ends tends to increase the energy. But we have a much more abstract situation than this elementary example. But it's a general Hilbert space fact that if A is an extension of B, then you get an inequality like this, where delta corresponds to A dagger A or B dagger B. Remember, delta was S dagger S for either U or V. So we're exactly studying this kind of situation. One operator S is SU is an extension of the other operator SV, and the general Hilbert space statement in that situation is this inequality, which we're now about to prove. Any questions on that? Yes?
So will you only act on vectors which are like in this, like on which V acts, I suppose?
No, actually, the beauty of this formula is that 1 over t plus a dagger a is a bounded operator because it's less than 1 over t. So it's defined on all Hilbert space vectors. See, a heuristic version of the statement. I didn't make the heuristic version, but the heuristic version of the statement is that b dagger b is bigger than a dagger a. The trouble with that statement is that there are domain issues, so it's hard to define precisely. We didn't need to define it precisely, so I was skipping it. The statement we actually need is this, and it does not have domain issues because both operators are bounded operators, so they're defined on all Hilbert space vectors. Any other questions?
Could you just reiterate why is it not like always equality if like one is an extension of the other and like you want to define?
Well, I tried to show it wasn't an equality by giving an example. So look at these functions on the unit interval. Let A be the d by dx acting on all smooth functions. B is d by dx acting on smooth functions that vanish on the boundary.
Yeah.
First, you know the operators are different. And you can see that A is a proper extension of B. It's an extension, but it's not the same. It agrees with B where B is defined, but it's defined on more vectors.
Yeah.
So then when we construct the Laplacian, A dagger A or B dagger B, it's like a quantum mechanics problem where we relax the condition on the wave function when we go from B to A. If you go through carefully the definition of Hilbert space adjoints, you'll learn that A dagger A is the Laplacian with Neumann boundary conditions, B dagger B is the Laplacian with Dirichlet boundary conditions. So they have different eigenvalues, and one of them are sines, one are cosines. And the sines have bigger eigenvalues, bigger energies than the cosines. A precise statement is this one.
But saying these different boundary values, aren't they like different spaces then? Or?
Well, that's the question that I was asked a moment ago. The two Laplacians, B dagger B and A dagger A, well, first of all, they're defined on the same Hilbert space. The Hilbert space is L2 functions on the interval. But no unbounded operator is defined on all vectors. So the two Laplacians have different domains. And therefore, to say that B dagger B is bigger than A dagger A is only a heuristic statement, which I avoided making, except that one of the previous questions led in that direction. Here, we avoided any domain questions because the two operators, 1 over t plus A dagger A. You see, if t is a positive number and also b is positive, 1 over t plus b is positive. So these operators are bounded above by 1 over t. So being bounded, they're defined for all Hilbert space vectors. You could initially define 1 over t plus A dagger A on states where A dagger A is defined. But then since it's a bounded operator, it uniquely extends over all vectors. So, well, you'll see in the proof. You're going to see in the proof in a moment that we don't have to worry about where anything is defined.
So maybe my question is just like how does the Dirichlet
It doesn't.
It does not.
No. That's why the statement that one operator is bigger than the other is heuristic. But this statement is well behaved. Because,
does this mean that there's the one operator is they assign 0 to that one? Or?
well, no. Okay. B dagger B, okay. The Dirichlet-Laplacian can't act on an operator that doesn't satisfy, a state that doesn't satisfy Dirichlet boundary conditions. But 1 over t plus B dagger B can. The way you do it is you can approximate any state by states that do obey Dirichlet boundary conditions, so it acts. And then you need to make sure, when you take the limit, it still acts, keeping you in Hilbert space. And that will work because this is a bounded operator. It will not work for B dagger B. If you take the Laplacian with Dirichlet boundary conditions and want it to act on a function with Neumann boundary conditions, you could introduce a little cutoff and it will act on that. But when you try to remove the cutoff, you'll end up out of Hilbert space. Here, because the operators are bounded, you're not going to end up out of Hilbert space.
I see. Thank you.
You see, that's a completely general statement. If you have an operator that's densely defined and also bounded, there's never a problem in taking a limit, so it acts on all vectors. Any other questions?
So you just need to use a method that usually work again. Both of them are again.
Well,
So that you can
I haven't proved this inequality yet. But in the case of Dirichlet and Neumann, you kind of know it, and it has a nice path integral proof, actually. I mean, you know it heuristically, I think, that Dirichlet tends to increase the energies. You might not be familiar with the statements, but it does have a nice path integral proof, although I wasn't planning to present it. Any other questions? Okay. So we have to prove this general Hilbert space statement, although I'll continue with the terminology we were using. But you'll see that I won't use any properties from here, except that SU is an extension of SV. SU being an extension of SV means that KV is contained inside KU. Right? One of them KU consists of pairs X and SU X, and KV is pairs X and SVX. So therefore, KU is contained inside KV, because every such pair is a pair of this kind. So we have KV contained inside KU, contained inside H plus H bar. Now we can define orthogonal projection operators. So we define pi, maybe we'll just call it pi u, is the projection on KU, and pi v is the projection on KV. So one is a projection on a bigger subspace than the other. And that leads to a trivial inequality. Pi v is equal to less than pi u. Which means that for any state lambda, lambda pi v, lambda is equal to less than lambda pi u, lambda. One of them gives the probability that a state in lambda would be measured to be in V. The other gives the probability that a state in lambda would be measured to be in the bigger subspace U. So this is a trivial inequality. We're going to see that the inequality we want is a consequence of this trivial one for the right choice of the state lambda. What happened? Oh. So we define an operator TV from H to H plus H bar that takes X to X plus SV of X and TU similarly takes X to X plus SU of X. So, if you range of state in H plus H bar as a column vector, so TV taking H to H bar, to H plus H bar, you could represent by a matrix 1 and SV. And so TV dagger would be a row matrix 1 and SV dagger. And I claim that pi v is TV dagger 1 over, the TV 1 over TV dagger TV times TV dagger. Oh, okay. I should have said that TV by definition maps H to the subspace KV inside H plus H bar. Right? TV was defined so that acting on any vector, it maps us into the subspace. So since TV maps us into the subspace KV, this operator maps any vector into KV, right? Because it has TV on the left. But you can also see two more facts. So first of all, TV maps H plus H bar into KV. Second fact is that TV squared is TV. And the third fact is that TV is TV dagger. So those facts are all immediate from the definition. If you try to square TV, you'll see a lot of things cancel out, and you'll get, if you try to square pi v, rather, with this definition. Sorry. Sorry. Okay. These are all statements about pi v, not TV. Sorry. So pi v maps the Hilbert space to the image of TV, which is KV, because there's a TV on the left. Then if you try to calculate pi v squared, you'll see you'll get, what would be pi v squared? It'll be TV, 1 over TV, dagger TV, TV dagger. Then we have the same thing again. And we can cancel a factor, and we get pi v. Similarly, if you take the adjoint of pi v, you would just multiply all the same factors in the opposite order, and that would give the same thing again. So you have an operator that maps this space onto KV. Maybe I should say by saying that pi v applied. Anyway, what I've called pi v is the orthogonal projection operator. This is the formula for pi v. Now, to calculate what is 1 over TV dagger TV, you see TV dagger was a row vector, TV was a column vector. So TV dagger TV is 1 SV dagger times 1 SV. So it's, sorry. So it's a little 2 by 2 matrix. Sorry, I think I've done that wrong. That's got to be wrong. Sorry. I've multiplied. Sorry. Does that look better? Okay. That also is going to work better with the proof we want in a second. So pi v is TV 1 over 1 plus SV dagger SV times TV dagger. And the same would of course apply for u. So pi u is TU 1 over 1 plus SU dagger SU times TU dagger. Okay, now we're almost done. Now that we have these formulas, we just are going to use the inequality for psi hat of a particular kind. Psi hat will be psi 0 in H bar. So I think I erased TV and TV dagger, but well, I didn't quite prove that the image was all of KV, but I think if you think about it a little bit, that'll be clear.
Okay, yeah, so say, okay, yeah, you can set 1, 2, and then with the other properties, then it has to be that.
Once we know that it's the projection onto all of KV, the rest is the proof. I don't think it's hard from what we had to prove that it projects onto all of KV, but strictly I only said it projected into KV.
Mm-hmm. Okay, thanks.
Mm-hmm. I don't want to try to fill that gap right now because I might get confused. Now all we're going to do is evaluate this inequality between states of this kind. And when we do that, you see the SV dagger term in TV goes away. In TV dagger goes away because it acts on the 0. And then on the ket, the same thing happens. On the ket, the non-trivial term on TV won't act because of the 0. So this matrix element is just the expectation value in psi of 1 over 1 plus S dagger U S U V S V. So we got the inequality we wanted with t equals 1. But there was nothing special about one. The only facts we used about SU and SV is that one is an extension of the other. So if I'd replaced SU by SU over the square root of t, and SV over the square root of t, we'd have gotten the same inequality with a 1 over t multiplying both operators. Or in other words, we would have gotten the inequality we want with t. So we're done. As expected, it took longer than expected, but anyway, we're done. Now, you can imitate this proof for a standard finite quantum system. I decided not to present it in class, but I think it's in section 4.3 of my lecture notes. The one called Some Entanglement Properties. Part of the reason I decided to present this rather than the analogous proof for a finite quantum system is that I actually think it's a little bit more obvious, because the basic fact we used is that going from V to U relaxed some conditions on the quantum mechanical wave functions, analogously to not imposing Dirichlet boundary conditions. And the proof for a finite quantum system, if you know this proof, you can figure out how to imitate it. Well, the proof in the case of, this kind of proof basically goes back to Petz. It's presented in a book by Petz and Oya, and I learned it for the finite quantum system from a paper of Petz and Nielsen. To my taste, the proof is more obvious in quantum field theory than in any other setting, because it's so obvious that SU is an extension of SV. So, any other questions about this? Yes?
I guess when you originally defined TU and TV,
yes.
Are they only densely defined on H? Do you have any issues?
They were only densely defined. They were defined on the domains of V and U, SV and SU, respectively. Well, sorry. Let's make sure that's true. Oh, for T, yes. But of course, the projection operators pi are defined everywhere. What happens is that they had TVs, they had as many T's in the denominator as the numerator, so they end up being bounded. Any other questions? Okay. I'm tempted to cheat slightly and tell you the following. Suppose you want to prove monotonicity of relative entropy from an ordinary quantum system. So we have a bipartite system A and B, and they're in two different laboratories. But clever experimentalists have managed to achieve quantum coherence between widely separated states. And they're doing experiments that are even letting them, in principle, measure this relative entropy. And they want to show that the relative entropy in the combined regions is more than that in region A. Now, as a quantum field theorist, I note that whatever they think they're doing is really happening in quantum field theory. So I just draw region V here and a region U here. And I say, therefore, this proof applies to arbitrary quantum systems. Well, there's a slight flaw here, which is that you need to generalize the proof I gave you. Because if you think carefully about this, what kind of states are involved here, you'll see that you'll run into states that aren't cyclic separating. So you need to slightly generalize modular theory to the non-cyclic separating case. And then you can indeed, I'm pretty certain in the book of Petz and Oya, you'll find how to generalize. They don't use the quantum field theory language, but they use the modular language. You'll learn how to generalize it. But there is some work involved in adapting, in using this picture to get a proof that applies for a standard quantum system. And because that was the case when I wrote section 4.3, I didn't do it that way. So No more questions? Okay, then for the rest of this week, we'll be doing as much as we can of 3 applications that I've already mentioned to you. Which are the Bekenstein bound, the C theorem in 2 dimensions. We'll only do the 2-dimensional case, and the ANAC. So these are our next goals. We'll see how far we can get this week. But first I have to explain the context for the Bekenstein bound. I could just state what the bound is supposed to be, but the background to it will anyway be something we need as a background for black hole thermodynamics. So we might as well discuss the background right now. So this goes back to 1972. Bekenstein's advisor was John Wheeler, who encouraged Bekenstein to worry about questions like the following. The second law says that entropy, S, is always increasing. But Wheeler observed that you could toss a cup of tea into a black hole and the entropy would disappear. Well, Bekenstein and Wheeler, of course, knew that energy had been redefined many times. It was extended. There was potential energy, chemical energy. Heat was eventually understood to be a form of energy. And then it was understood that rest mass is a form of energy. So energy conservation had persisted, but only through enlarging the concept of what is energy. So Bekenstein had the idea that the concept of energy could be generalized. Sorry, the concept of entropy could also be generalized so that the second law would be valid even in the presence of a black hole. So Bekenstein wanted to define an entropy of a black hole which he imagined would count the number of ways the black hole could have formed. And the entropy was supposed to be such that the generalized entropy equal to the black hole entropy plus the ordinary entropy outside is always increasing. So, in particular, he needed to assign to the black hole. See, the black hole might be possibly interacting with very low entropy matter. So whatever the black hole, you can always have a situation where S out is negligible. So, on the other hand, the black hole could also swallow up a lot of entropy. So S black hole is going to have to be very big if this is going to be a universal principle. So Bekenstein wanted to define a property of the black hole which is always increasing. Now, you might naively think that the energy or mass of the black hole is always increasing, but that's actually false. If you have a spinning black hole and you toss in matter with opposite sign of the angular momentum, you can slow down the spin of the black hole and make the mass go down. This had been shown by Penrose and elaborated by Christodoulou shortly before Bekenstein was working. So it was known that it's not true that the mass always increases. However, partly probably inspired by Christodoulou's observations on what Christodoulou called the irreducible mass, Hawking had just discovered the area theorem, which we proved in this class about 6 or so weeks ago. So Bekenstein knew that the area of the black hole is the quantity that always increases. The area, well, A, which is the area of the black hole horizon, does obey an area theorem. It's always increasing. So it was fairly natural for Bekenstein to propose that a multiple of the area with some constant that Bekenstein didn't know times the area would be the entropy of the black hole, except on dimensional grounds, Bekenstein knew that there had to be a 1 over g h bar. Now, the 1 over g h bar, I will usually set h bar to 1, but I've written it there for two reasons. One is that we're later going to discuss the derivation by Gibbons and Hawking of this formula where it's natural that the black hole entropy has a 1 over h bar in it. But the other reason is that that 1 over h bar, which is, of course, h bar is small, so 1 over h bar is very big in everyday terms. It goes into explaining why black hole entropy is enormous. For example, it turns out that the entropy of a black hole with the mass of the sun is about 10 to the 20 times the entropy of the actual sun. Anyway, Bekenstein didn't know this constant, but as we'll discuss in probably the last week of the course after Thanksgiving, Hawking learned that k is 1/4. So the modern formula for the black hole entropy is this one. And then Bekenstein said that, well, without improvement of what Bekenstein said, the generalized entropy is A over 4 GH bar plus the ordinary entropy of matter and radiation outside the black hole. So Bekenstein visualized S out as thermodynamic entropy, and therefore his formula only made sense near equilibrium. More modern approaches understand that S out should be defined in general as von Neumann entropy. That's one of the main reasons we studied the von Neumann entropy in this course. And Bekenstein's proposal, which was the generalized second law, was eventually proved by Aaron Wall, only in the last decade, I think. And that's more or less the last result we'll get to, probably in the last lecture. Well, when we present the proof, we'll discuss exactly what it shows. I don't want to, most of the audience isn't familiar with the proof, so I don't want to discuss that now. Anyway, a version of this was proved about a decade ago, and we will discuss that proof. Now, Bekenstein made some tests. Well, before making some tests, let me also write some formulas. Let's consider the example of a Schwarzschild black hole. The area, it's round, so the area is 4 pi r squared. R is 2gm, where m is the mass. So the entropy I think it's 4 pi gm squared plus S out. Then starting with this formula, well, I'll just explain a simple example Bekenstein considered. Suppose the black hole absorbs a photon of wavelength lambda, so the energy of the photon is 1 over lambda. Now, S out will go down by whatever entropy the photon was carrying. And that's an amount of order 1, because at the minimum, the photon has 2 polarization states. And we might worry about its position, but that won't change very much. So S out, delta S out changes by an amount of order 1, well, at least of order 1, but not much bigger. Bekenstein actually considered black body radiation incident on the black hole. And the entropy per photon is of order 1 in a black body, which maximizes the entropy in a large collection of photons. Anyway, delta M is the energy, which we said is 1 over lambda. So the change in Sgen is 8 pi, well, I'm going to assume that the black hole photon is much less, I'm going to assume that delta m is much less than m. So I work to lowest, first order in E. So we get 8 pi gm E minus 1, let's say. That's a very rough estimate of delta Sgen. So, replacing 2 gm with the black hole radius and E with 1 over the wavelength, we find that delta Sgen is, I think, 4 pi r over lambda minus 1. So, if lambda is much less than r, delta Sgen is positive. So in other words, if the black hole is absorbing photons whose wavelength is smaller than itself, then the generalized second law appears to be true. But Bekenstein actually had a problem about which in his original paper what he said was quite unconvincing. Suppose that lambda is much bigger than r. In other words, consider the black hole interacting with photons whose wavelength is much bigger than r. Then delta Sgen is negative. So the generalized second law seems to be violated. Bekenstein had the nerve or courage to publish anyway, despite the fact that, at least when I look at the paper, what he said about this didn't appear to make much sense. And he was completely vindicated a year or two later when Hawking discovered what was going on here. What's going on here is that the black hole at the quantum level is actually radiating. And the radiation is strong for photons with a wavelength longer than the size of the black hole. So the photons that caused trouble for Bekenstein were the ones where each mode is heavily populated with outgoing Hawking photons. So what's happening here is that when the wavelength is short, you can ignore the Hawking effect. But where Bekenstein's discussion didn't make sense was where the Hawking effect is important. So we won't straighten this out until possibly after Thanksgiving, or maybe the last lecture before Thanksgiving when we discuss the Hawking effect. Anyway, that's what Bekenstein said in 1972, and it inspired Hawking to discover his famous effect of black hole radiation. But a decade later, Bekenstein came back to this and said the following, which I better look in my notes or I'll mess it up. So what he said, I would say, is quite heuristic, and it was followed by decades of confusion. I'll explain the reason for the confusion, and then I also will explain how the confusion was resolved. And resolving the confusion is the main point of what we're trying to get at. Suppose the black hole absorbs a body of energy E, entropy S, and size that I'll call curly r, because I've used regular r for the black hole radius. First of all, Bekenstein proposed that this is possible if and only if curly r is less than the black hole diameter. The capital D is the diameter of the black hole. So you might not find that convincing. An object bigger than the black hole perhaps can be crushed gravitationally and then get absorbed by the black hole. But anyway, let's follow along and see what Bekenstein was led to propose. So when the black hole absorbs this body. So we'll again assume that E is much less than m of the black hole. Delta S gen, I hope we didn't erase it. It's 8 pi gm times E of the body, but minus the change in S out. Delta S out is just S of the body. Whatever the body was, it fell down the hole, and that entropy disappeared from the outside world. So let's write it in terms of the diameter of the black hole, which is twice the radius, or 4gm. So the generalized second law says that 2 pi dE minus S is equal to or bigger than 0 if D is equal to or bigger than the size of the body. At least that was Bekenstein's proposal. See, he puts the condition that D should be bigger than the size of the body because he proposes that otherwise the body isn't absorbed by the black hole. So for this to be true whenever D is bigger than the size of the body, we need 2 pi RE minus S equal to or bigger than 0. And as Bekenstein noted, this statement has nothing to do with gravity or black holes. So Bekenstein proposed this statement as a universal bound on anything that exists in the universe, on any body, let's say. And I'm not sure how precise Bekenstein was about whether this was supposed to. Okay. I'm not exactly sure how Bekenstein phrased this, but later authors were not sure whether this was supposed to only apply to the real world or was supposed to be a completely general quantum field theory statement. So that's a question about the interpretation. Does it only apply to things that exist in the real world or things that exist in any quantum field theory? Well, there seems to be a trivial reason that it can't be true in an arbitrary quantum field theory. Consider a free field theory with n free fields, let's say free scalar fields, of mass n. And now consider a box with one particle. So the size and the energy of the box are independent of n, but the entropy grows like log n plus a constant, because you could put any of n particles inside the box. So it seemed, and I certainly am one of those who accepted this at face value, it seemed that 2 pi RE, well, okay. it seemed that for any constant k, the reason I'm generalizing from Bekenstein's 2 pi to an arbitrary constant is that the derivation was so heuristic that you might think the idea is correct, but the constant 2 pi is wrong. But this example seems to show that for any constant k, k times Re minus s can be negative. Arbitrarily negative as n becomes large. So it looks hopeless for the Bekenstein bound to be a universal statement about quantum field theory. Well, that's a little bit disappointing, but you could retreat and say that the Bekenstein bound is only a statement about the real world. And here you could ask the following. So you could ask, if true, is the bound an interesting statement about the real world? Well, an interesting statement is an inequality that can sometimes be almost saturated. In other words, if the Bekenstein bound is true, but it's always satisfied with many, many orders of magnitude to spare, then it's not a terribly interesting statement about the real world. So let's try to find something that would come close to violating the Bekenstein bound. Well, we could take a box with a gas of particles, let's say a gas of photons, at temperature T. I could take atoms instead of photons, but they would have a rest mass, which would increase the energy without contributing to the entropy. So to try to minimize the energy for fixed entropy, I take photons. And then, as you may know, to maximize the entropy at fixed energy, you should actually take a thermal distribution. That's why thermal distributions are important. They maximize the entropy for a given energy. So if you have a box of size curly r and temperature T for a black body, the entropy will be of order RT cubed. And the energy is actually going to be of order the volume of the box R cubed times the energy density of the black body, which is T to the 4th. So then you'll find that the Bekenstein ratio, RE over S, so the Bekenstein bound with the lower bound, or what I'm calling the Bekenstein ratio, curly RE over S. The Bekenstein ratio with these numbers comes out to be TR. Well, for thermodynamics to make sense, TR is much bigger than 1 when thermodynamics makes sense. You have to have photons of shorter wavelength than the size of the box so that at thermal equilibrium there will be many photons in the box, and then thermodynamics makes sense. When thermodynamics makes sense, the Bekenstein bound isn't very interesting because it's satisfied by a wide margin. Well, what can we do to make the Bekenstein bound not be more interesting? Well, we could reduce the temperature to 1 over R to improve the situation. But then the box only contains 1 or a few photons. So we can't really use thermodynamics. But since Bekenstein proposed that this was a universal bound, we can still talk about it. The only trouble is we might not know what's meant by entropy. when thermodynamics isn't valid. But since we've studied von Neumann entropy, maybe that won't bother us. What might bother us, though, is that we have the box here. And the mass of the box might not have been very important for a big box, but it is going to be important for a box that only contains one or a few particles. And the mass of the box contributes to the energy without contributing to the entropy. So it will be better to get rid of the box. So we consider one particle without the box. So the most interesting case for the Bekenstein bound is something like a single particle not contained in a box. And the trouble with that is that, well, it's not clear what is the size of one particle without a box. That's fuzzy in relativistic quantum mechanics. But worse, it's even less clear what is the entropy of one particle without a box. So this looked, well, speaking personally, it looked to me like a rather unproductive direction that wasn't going anywhere. And it went on like that for a quarter century. But this period of confusion came to a rather abrupt end when H. Cassini, in 2007, gave a precise statement and proof of the Bekenstein bound. So I would say Bekenstein hadn't really had a precise statement, because when his bound is interesting, it's not very clear what you mean by either the size or the entropy of the system. Any questions on what I've said? No questions? So what did Cassini do? He looked at Rindler space. So time goes up, x goes to the right. He considers observations of an observer limited to the right Rindler wedge. So we'll work in region U. And we're going to Cassini's insight was that the Bekenstein bound should be interpreted as positivity of relative entropy. To be more precise, he considers two states. One is the vacuum state, and the other is any state. The Bekenstein bound is supposed to apply for any body, according to Bekenstein, which Cassini interprets as being that the bound is supposed to hold for any state in any quantum field theory. So omega will be the vacuum state of a quantum field theory, and psi is going to be any state at all where we want to prove the Bekenstein bound. Now there's something we've proved is positive. We know that the relative entropy between these states is non-negative. And Bekenstein had the insight, Cassini had the insight, which I think was really quite remarkable, that this positivity is a version of the Bekenstein bound. Now, to explain that, we're going to leave the rigorous world a little bit. And we'll write down some slightly ill-defined quantities that we'll renormalize. So this is rigorously defined. You could carve this statement in marble if you wish. As Einstein used to say, speaking of the left-hand side of the Einstein equations. But now we're going to get our hands a little bit dirty interpreting it. We're going to introduce density matrices rho and sigma for the state psi and omega in region U. The only region I'll consider will be the right Rindler wedge. So I won't keep writing U all the time. That will always be the region. I could call it rho U and sigma U, but I won't because U will always be fixed. But one thing which we will use is that we computed in one of the Zoom lectures that sigma is the exponential of minus 2 pi times what I've usually called Kr. Kr is the one-sided Lorentz-Boost operator. And now I'll make explicit that there could be some normal coordinates. I usually leave them out, but I want to, Cassini's discussion is in d dimensions. So there are 2 dimensions in the picture, but there also are some normal coordinates, y perp. They just go along for the ride in the formula. You integrate over them. So the relative entropy for region U between the 2 states is the trace of rho log rho minus the trace of rho log sigma. But we're in a situation, quantum field theory, where the density matrices are not really applicable. And it turns out that both of these expressions are divergent. Of course, the left-hand side is well-defined, because we had a perfectly well-defined formula for it in terms of the log of the modular operator. It's up there. But when you try to write it this way, you run into the fact that density matrices are ill-defined. But Cassini improved the situation by adding and subtracting something from both sides. He added and subtracted traces sigma log sigma. Well, what have we gotten now? Trace of sigma log sigma is the entropy. This is the entropy of the vacuum in region U. And this is the entropy of psi in region U. Now, as I've explained, entropies are ultraviolet divergent. But the divergence is common to all states. Because every state looks like the vacuum at short distances. So this difference is finite, or at least it's potentially finite. It's typically finite, although you can find situations where it's not finite, which is related to the fact that the relative entropy can be plus infinity. But unlike the 2 entropies separately, this difference has got a decent chance of being finite. And we'll call it minus delta S, minus the entropy difference. You see, formally, it's minus the entropy. Well, because of the plus sign here, this is minus the entropy in region U. This is plus the entropy with the minus sign. It's plus the entropy of the vacuum. So if I let delta S be the entropy of psi minus the entropy of the vacuum, this thing is minus the entropy difference. Here, on the other hand, the definition of a density matrix was that trace of rho log sigma is the expectation value in the state psi of the operator log sigma. And similarly, the trace of sigma log sigma is the vacuum expectation value of log sigma. That just says that rho is equal to rho psi, and sigma is equal to sigma of omega. These statements here are just the definition of density matrices. So we manipulate it into this form. But now we use the fact that minus log sigma is 2 pi times k right. That's just the logarithm of this statement that I wrote over here, which we computed in one of the Zoom lectures. So therefore, we learned that the relative entropy between psi and omega is minus the entropy difference plus 2 pi. Well, one term is going to be the expectation value in the state psi. The other term is the vacuum expectation value of the same thing. So we get this formula for the relative entropy. Well, as you probably know from your study of quantum field theory, T00 is a subtle operator to define. It needs renormalization. In free field theory, if you compute the vacuum expectation value of T00, you'll get a cortically divergent expression that's usually renormalized to make the expectation value of T000 in the vacuum. But that does require renormalization. The renormalization is an additive constant. Since we're subtracting the expectation value of T00 between two states, the additive renormalization of T00 doesn't matter. So the expression is well defined, irrespective of that additive renormalization. But one usually picks a renormalization. The usual renormalization is such that the vacuum expectation value of T00 is 0. So that defines, that state condition is needed to define what we usually mean by T00. Up to this point, the theory had no way to know that that's what we were going to mean. But now we say that that's what we mean. So we can get rid of this term. And so what we learn is that 2 pi times the expectation value in the state psi of this integral and Cassini's insight was now, well, suppose we take a semi-classical state that's localized, well, suppose it's localized at some position in the Rindler wedge, a distance x from the origin. Then x will be approximately a constant, so this integral will be approximately the expectation value of x in the state psi times the energy of the state psi. So that inspired Cassini to say that this is the correct version of R times E. It's a measure of the size of the body. Well, when semi-classical intuition is good, It's a rough measure of the size of the body times its energy. And anyway, this is the version of the Bekenstein bound that's true. 2 pi times this version of R times E is equal to or bigger than the entropy difference between the state and the vacuum. Okay, people are starting to open the door because of the next class, and I've woefully run over. So I'll take a very quick question if there is, and we'll discuss the formula a little bit more at the beginning next time. No questions now? You don't have to rush that fast. You can ask a question.
But why is not this the average position of the state, or whatever we call it, rather than?
Well, this is a measure that has dimensions of energy times mass.
That's for sure.
And if you try to make it as small as possible, to make the bound as challenging as possible, you'd move the body closer to the origin as much as you could. So this is of the order of magnitude of R times E. Bekenstein didn't define R times E precisely. So Cassini defined something precisely, which is similar to R times E, and Cassini found the version of the Bekenstein bound that's well-defined and true. Cassini also, in a later paper, proved another version, but since the ideas are similar, I won't explain that second version. Any other very quick questions? Because we do have another class coming. Okay, we'll discuss the formula a little bit more at the beginning next time.